خب بسم الله الرحمن الرحیم. امروز روز شنبه هست 17 اردیبهشت ماه 1401 جلسه هشتم درس زمین آمار در خدمت عزیزان هستیم. Perhaps it might help to have a brief discussion of what we have in our previous lectures on Monday, and then move to the next step, which is grammar. If you remember, we try to have a general problem statement saying we are given a single partial realization of a random function, and then we are asked to estimate the attribute under consideration at the point which is not sum. That is the general problem statement. And then we argue that if we want to solve this problem, we have to consider 3 steps: exploratory spatial data analysis, variogram modeling, and then estimation. For the last 2 or 3 sessions, we focused on exploratory spatial data analysis. The first topic that we considered was univariate description. In univariate description, we ignore the spatial variation as if instead of having a single partial realization of the random function, we have a multiple realization of a single random variable. And then we consider these multiple realization of a single random variable to be purely random, trying to prepare histogram, probability plots, touch on measure of location, measure of dispersion, measure of skewness, measure of kurtosis, and so on. And then for this part, we argued that the book written by Isaac on Introduction to Geostatistics, as well as the book written by Kitandis on Introduction again to Geostatistics, would help to dig further into univariate description. And we gave a 14-page document or shared a 14-page document to you via email touching on exploratory spatial data analysis. And if you have a chance to look at the manual of ArcGIS, there is a module in ArcGIS, so-called geostatistical modules. And in that document, again, you have a bunch of material on exploratory spatial data analysis. Then when it comes to multivariate or bivariate description of our data, it seems that instead of having a single partial realization of a random function, we have more than one random function. And we would like to consider if there is any correlation between our primary variable, say precipitation, and secondary variable, say elevation. We argue that we have to have 2 conditions for justifying co-kriging instead of kriging. The very first condition is to have a common information between primary variable and secondary variable. That is the first condition. The second condition concerned with ease of monitoring the secondary variable compared to primary variable. For sure, you could justify co-creating for estimating precipitation given precipitation and elevation, or estimating suspended solid, being able to have both suspended solid and turbidity. And when it comes to groundwater hydrology, you could go ahead and talk about estimating piezometric head, assuming that you would like to consider your piezometric head to be primary variable and hydraulic conductivity or storativity or transmissibility to be your secondary variable. And then quantitatively, by bivariate discussion, we try to talk about QQ plots. In QQ plots, we consider each point on your QQ plot to share the same probability of accidents. It really doesn't matter whether you have the same data set on primary variable and secondary variable. Your secondary variable could contain n stations, and your secondary variable could have very different, such as m stations. They could be either co-located or not co-located, having the same spatial location when you want to prepare QQ plot. And by QQ plot, you could manage to touch on nature of probability density function or cumulative distribution function, which could be attributed to each variable or random function. And then we talked about PP plots. In PP plots, we try to map probability of accidents for both primary variable and secondary variable, and each data point on our PP plot will share the same spatial location. It's quite important to acknowledge that. QQ plot will be contrasted with PP plot based on the nature of common information. In QQ plot, each data point shares common probability of accidents. In PP plot, each point shares spatial location instead of probability of accidents. In fact, probability of accidents is very different for each data point in PP plot, while it is the same in QQ plot. And then we talk about Pearson correlation coefficient, or traditionally we call coefficient of correlation in statistics. And finally we talk about Spearman correlation coefficient. Both Pearson correlation coefficient and Spearman correlation coefficient should share the same spatial location. In Pearson correlation coefficient, you will try to compute correlation coefficient using original data. In Spearman correlation coefficient or random correlation coefficient, you will try to compute coefficient of correlation using the range instead of the original values. On our Mondays, for which number of the students did not manage to take part in our class, we touch on spatial description. When it comes to spatial description, at first, we try to touch on nature of data. Because when it comes to spatial description, we could talk about nature of spatial data. What do I mean by nature of spatial data? Whether our data are regularly based or irregularly based. By just preparing location map for our data, we could assess, evaluate the nature of our data, and we have, fortunately or unfortunately, depending upon the nature of your background, you have different name for the nature of data. Ground-based versus air-based is one possible name attached to nature of data. Vector-based versus raster-based. Regular-based versus irregular-based. And then point-based versus block-based or pixel-wise data. Of course, when you talk about ground-based, sooner or later you will realize that you are talking about vector-based data, or you are talking about irregular-based data, or you are talking about point data. When you are talking about air-based measurement, whether it could come from radar or satellite, raster-based, regular-based, block-based are typical name assigned to air-based measurement. By just preparing location map for your data, you could assess which part of the domain monitored sparsely and which part of the domain monitored densely. Unfortunately, in any geostatistical program like ArcGIS or GS Library or whatever program that you have at your disposal, the program will try to assign color to each data point. And there is a legend connected to those colors. If you want to explore trend in your data, drift in your data, location map would help you spatially to decide whether your data contain any trend or not. If it happened that the color changes gradually as you move from north to south, or as you move from, say, west to east, then that means you have some sort of non-stationarity in your data, which means that either your mean or your variance depends on spatial location. They are not constant. And then contour map, where you are familiar from topography map, it's another way to assess the degree of variability, spatial variability in your data. When your contour map are quite dense, very near to each other, that means the degree of variation is quite high. If it happens that your contour map is quite sparse, very depart from each other, then that means that the degree of variation in that part of your study area is quite low. Symbol map, indicator map, or some other way to describe your data qualitatively. I recall when I did my PhD program research, I have to map depression storage over a typical plot 1 meter by 1 meter. Which means if I pour water over my study area, which part of my study area will be covered by water and which part of my study area would not be covered by water. I have to map those areas. If you look at any book written on hydrology, engineering hydrology, you could barely see a single paragraph on depression storage. Even if I ask you what is depression storage, the only thing that you can say is calculation. Nothing more than that. That took almost 4 years of my life to dig further into depression storage. And at that time, the name of ArcGIS was ArcInfo in 90. And I have a chance to work with this program not on Microsoft. Currently, nowadays, ArcGIS can be executed using Microsoft At that time, almost 25 years ago, you can only execute this program on Linux or Unix. And I recall at that time I used a module so-called grid to map, at first try to delineate depression storage digitally, not graphically. And then as soon as I delineated the depression storage, which pixels belong to depression and which pixels that does not belong to depression, I have to ask for help the program to denote pixels belonging to depression with 1 and pixels which do not belong to depression by 0. And that 0, 1 would differentiate between pixels belonging to depression and pixels that don't belong to depression. And then we publish our first paper extracted from dissertation on Journal of Hydrology, and in that paper we try to address the impact of spatial resolution on mapping depression storage. It's quite interesting for you to justify why hydrology textbook cannot quantify depression storage. Out of your surprise, we did realize that mapping depression storage is scale dependent. If you look at, I would like to talk about the scale dependent a little bit more. If you look at this part of this blackboard, you will consider to be homogeneous, yes or no? But if you change your glass, instead of having nothing on your eye, try to have a better resolution instrument to look at this part of the table. Then out of your surprise and my surprise, as soon as you change your glass to look at this part of this blackboard, you will see that it is heterogeneous. What does that mean? That means depression storage is quite grid or scale dependent. It depends upon the grid spacing. If you monitor the surface with 3 mm by 3 mm grid spacing, then you are going to have a huge number of depression storage. If you start to increase the grid spacing, then the number of depression storage over the surface will decrease. And it's quite interesting for you to acknowledge the fact that if you map your number of depression on y-axis and the grid spacing on x-axis, the relationship is going to be linear. And this linearity implies that the relationship between number of depression storage and grid spacing is parallel, fractal geometry. And then when it comes to surface area at pool point, volume of depression at pool point, maximum depth of depression at pool point, again they have a parallel relationship with each other. Look at regular fractal that you are familiar with. Depression storage are irregular, random fractal. When it comes to regular fractal, look at these three relationships. Perimeter of a circle, area of a circle, and volume When you want to use either of these equations, you will not ask yourself whether your staircase is small or large, yes or no. No. This equation, these relationships are very applicable to any circle. For line object, the power is 1. For aerial object, the power is 2. And for volume, the power is 3. And when it comes to a paper that I shared with you in my interview with a newspaper magazine so-called Fresh, you will have a chance to read that interview. We try to connect topographic variation with the day of judgment. You might have a chance to read the entire paper where we try to extract that paragraph toward conclusion section saying that these are regular fractals, and then when it comes to irregular or random fractal like depression storage, again the relationship is power law. This is power law. If you call any of these to be, say, y, and then this is power law. For linear object, you could have these. For aerial object, you could have these. And then when it comes to irregular or random fractal, this power here is not a whole number, integer number, like 1, 2, 3. When it comes to random fractal, this V here is less than 1 or greater than 1 depending upon the nature of the object. You have another item in your hydraulic course, and that has something to do with Vs. Result. Again, the overall relationship is this. Y is going to be your discharge, X is going to be the height on your weir. You could have this, where the power is 1. This weir is called Cipolleti weir, where the power is 1. You could have Q equal to AH to the power of 1.5, and this corresponds to rectangular weir. And then you could have Q equal to AH to the power of 2. This corresponds to parabolic weir. And then you could have AH to the power of 2.5 when your weir is triangular. Parabolic. And when it comes to proportional weir or Cipolleti weir, we have a situation like this. This is triplet wear, where the relationship between discharge and height on your wear is 1. These are 4 types of wear, where again the relationship between 2 variables is powerful.
اولی سر چجوری بود؟
از اینجا رد میشه. These are I'm not quite sure if we have it in our hydraulic laboratory. But the water will move in this direction. It's quite attractive to be able to connect these ideas to data assimilation. By the way, tomorrow, Dr. Hamid Moradkhani from Department of Civil Engineering, Portland University, and then Oklahoma University will try to touch on drought, and his expertise is data assimilation. And I invite everybody to take part in that meeting. It is in the afternoon, tomorrow afternoon. Prolific writer in particularly hydrology, for which we need to dig further into this discipline. Now, that is for something which I did not cover in my previous lecture on Monday. When it comes to quantitative spatial description, we have a number of possibilities to describe our data spatially and quantitatively. The very first tools to consider is H-scatter plot. We can plot H-scatter plot regardless of the nature of data. You could plot H-scatter plot for regularly based data, raster based data. You could prepare H-scatter plot for irregularly spaced data. And then the next item to consider is to go for plotting measure of similarity. And for measure of similarity, we have either correlation function, experimental, either omnidirectional or directional, correlation function, we could have experimental, omnidirectional, or directional covariance function, these two measures are measure of similarity. And then we have experimental, either omnidirectional or directional variogram function. Today, I would like to tell you one more thing which we did not cover on Monday, and that is where this equation is coming from. Remember, when we started to touch on HS-scatter plot, we considered two types of data. And it's quite important to differentiate between HS-scatter plot for regularly based data, HS-scatter plot for irregularly based data. Because of the regularity in raster-based data, we prefer to start touching on HS-scatter plot for raster-based data. You have to freeze two things when you want to prepare HS-scatter plot. The very first thing that you have to freeze is the grid spacing. You have to freeze grid spacing, and then you have to freeze the direction to be able to go for preparing HS-scatter plot for a particular direction. And then the next question that you would like to raise is this: could it be possible to extract a single number from each scatter plot? We could have numerous HS-scatter plot for a typical raster-based data. What do I mean by numerous? By numerous, I mean when you want to freeze the grid spacing, you may want to freeze the grid spacing by H, or 2H, or 3H, 4H, and so on. And then as soon as freeze the spatial grid spacing, then you can count the number of pairs in a particular direction whose separation distance correspond to H, or 2H, or 3H, and so on. And then, could it be possible to extract a single number from each HS-scatter plot? And those single numbers which could be extracted from each scatter plot correspond to either measure of similarity or measure of variability. And when it comes to raster-based data set, we show that as you increase the grid spacing, two important things will happen. Please pay attention. As you increase the grid spacing, two important things will happen. The first thing is that as you increase grid spacing, the number of pairs associated with each HS-scatter plot will decrease. If you have a series of raster-based data, this is a typical map for raster-based data. And this is the grid spacing. which is the same as this. If you are asked to tell your audience this question, what is the number of pairs whose separation distance is h and they are in east-west direction? This is east-west direction. This is west, and this is east. And then that is the grid spacing, which is the same as this. If you want to count the number of pairs whose separation distance is h, and they are located along west-east direction, this is going to be the first pair, this is going to be the second pair, and this is going to be the third pair. And then you can go ahead altogether 9 pairs. You have 9 pairs in west-east direction whose separation distance is h. Now, if I use different color and try to delineate pairs whose separation distance is 2h, that's going to be the first pair whose separation distance is 2h and it is aligned in east-west direction, and this is going to be the second pair. Again, this is as you can see, if you increase the separation distance in west-east direction to 2h, then the number of pairs is going to be 6 instead of 9. If you keep going, use different color and talk about pairs whose separation distance is 3h. You could realize that if you fix your separation distance to be 3h and they are aligned in east-west direction, then you are going to have 3 pairs. What do I mean by H-scatter plot? You have to, when either of 1 scatter H spacing, 2H, 3H, and so on, you have to assign name to each pair when it comes to the numerical values. Of course, you know for sure that you have a pixel value at this point, pixel value at this point, pixel value at this point, pixel value at this point. And then if you want to map H-scatter plot for say H situation, then you have to tell your audience you have to connect this point to this point, and then call this tail, this point H. The numerical value of the attribute under consideration at P will be mapped on x-axis. The numerical value of the attribute under consideration at H will be mapped on y-axis. What if the separation distance is 0? Can you tell me the number of pairs whose separation distance is 0?
This one. No, it's
the number of points. 4 times 3, 12. If the separation distance is 0, then you have altogether 12 pairs. And quite interesting to realize that if you map your pairs for the case when h is equal to 0, they will correspond to the bisector of the first quadrant in صدر و بعد.
بسید یه سوال اگر توی همیشه فاصله دیستنس تفریقیمون قرار با 3h بود و همی دایرکشنال بود موقع تحت بگذاریم.
Then again we are going to have a situation where we have to consider. Please pay attention. If you are talking about omnidirectional, then that does not mean that you have to consider both this direction and this direction. It may happen that you have a data pair in this direction as well, with that separation distance. But if you want to have a quick answer to your question, then for the case when you have omnidirectional experimental either covariance or correlation or variogram, the number of pairs with separation distance is 3h. It's going to be 3. Because in this direction we have no pairs with separation distance is 3h. It may or may not, depending upon the geometry, could find pairs with separation distance is 3h at different directions. Look at
در اون صورت از وست ایکس اگر می‌داشتیم آیا از ایست به وست هم دوباره میتونستیم داشته باشیم؟ یا از جای پیل عوض؟
No. If you consider this to be your first pair, then it makes no sense to put it vice versa. Call this a T, call this T. In a sense, when you want to specify the direction, it's quite important to put west and then east. By putting this W here and E here, your vector should be directed from east to west, not from east to west. See? It's not possible to write or draw your vector in this way. This is east to west. You have to draw your vector from west to east. If you draw your vector from west to east, then that's going to be your tail, that's going to be your head. This could be mapped on x-axis, this should be mapped on y-axis. Therefore, no, you could not change the order, tail to head and then head to only one. And because of this, we argue that the distance matrix will be symmetric. If you take this point and then find the distance from this point to every point in your data map, then when it comes to this point and then you have to know the distance from this point to every data point, then it may happen that you have a symmetric matrix, not asymmetric matrix. Which means that the diagonal element is 0 because the distance between the point and the point itself is 0. And the off-diagonal element is symmetric. They are the same. Which means that if your dij is equal to dji, and then dii for distance matrix is 0. The second happening in your H-scatter plot, if you start to increase the separation distance, is this. When your separation distance is 0, the bandwidth is 0. Because every data point will be along bisector of the first quadrant. If you increase the separation distance, then the bandwidth, the fluctuation of data point along or around the bisector will increase. Do you know what I'm saying? For 0 separation distance, the bandwidth is 0. As you increase the separation distance, the bandwidth will increase. And then in our previous lecture, we tried to raise this question. Could it be possible to extract a single number from each H-scatter plot? And then we tried to answer that question for both regularly based data and irregularly based data. Today, at first, I would like to tell you where this equation is coming from. Let me start with again, if this is your y at, say, S I, this is going to be your y at S plus H, because you will increase the spatial location to S plus H. And then, if you consider a Cartesian coordinate system where you map your attribute under consideration at head here, the attribute under consideration at head here. This is H scattered plot when the separation distance is H. And then you have, this is the bisector of first quadrant. From here to here is the same as from here to here. Perhaps this line could be drawn in such a way that the angle could be or should be 45. This angle should be 45. And then you have a number of points for your H scatter plot fluctuating around this line. What does that mean? If you take a typical data point such as this point, from here to here is y at Si, A, and from here to here is y at Si plus H. Repeat this for other data point here. Then the question is, if you want to have a quantitative measure for these bandwidths, how could you proceed to establish this quantitative measure? به فارسی اشاره داشتم که اگر چنانچه شما شروع بکنید سپریشن دیستنس رو افزایش بکنید، برای زیرو سپریشن دیستنس پهنای باندتون صفره، چون تمام نقاطتون رو نیمساز رو به اول قرار میگیرن. با افزایش سپریشن دیستنس، چون تو هر هیچ کسیت اطلاعاتی دو تا چیز بیریزه، سپریشن دیستنس، جهت، دایرکشن. اگر چنانچه دایرکشنال، اگر دایرکشنال رو نخواهید اونی دایرکشنال باشه، اولا دیگه جهت هم فریز نیست. تو هر جهتی که مد نظرتون باشه، فعلا هم داریم نقل رگولر بیس دیتا صحبت میکنیم. بعد نقل رگولر بیس هم جلسه قبل نکاتی رو گفتیم، هم ترم قبل همین ترم هم باز برای رگولر هم صحبتایی داشتیم. سوالی که من میخوام بپرسم و دوست دارم یک کمی مانا گوش بدم، این رابطه که ما اینجا نوشتیم از کجا به دست آمده؟ measure of variability. Could it be possible for we as civil engineers to consider each data point to be a weight and try to obtain the moment of each weight around this axis, the second moment, of course not the first moment, and then take the average of that moment? If the dispersion, the bandwidth is quite large, then the average second moment of inertia is going to be large. If the data points are fluctuating near to this line, then the average moment is quite small. Assume that each data point here are weights, and then try to multiply each weight by the second or the square of this distance. Try to quantitatively compute the bandwidths by summing di to the power of 2, squaring each distance to the power of 2.
این خط بسفیت یا
No, that is the Newsov Barber. Trying to square each distance, perpendicular distance, and then divide by the total number. I will show that this relationship is this. Bandwidth is a measure of variability. As you increase the separation distance, the bandwidth will increase. If you decrease the separation distance, then the bandwidth will decrease. If you have zero separation distance, then every point will be along this line when the bandwidth is zero. If you increase the separation distance, then these measures, these di will increase, and their square will increase, and then you are going to have increase in your bandwidths. How could it be possible to convert this to this equation? If you this angle is 45, therefore this angle will be 45 as well. And then from here to here, is y at si plus h minus y at si. Okay? Because from here to here is this, from here to here is this, because from here to here is the same as from here to here. Therefore, from here to here is y at si, from here to here y. And then here is the first increment. Okay? And then if you consider this right triangle, you can say di is equal to this distance times cosine of 45. Because cosine of this angle, which is 45, is equal to this divided by di. This is for 90 degrees. Okay? Therefore, di can be written as y at si plus hk minus, or h, it really doesn't matter, minus y at si. You have to multiply this by cosine of 45 to get this distance dr. And then raise this to the power of 2, plug it here. Cosine of 45 is square root of 2 divided by 2 times y at si plus h minus yh. Raise this to the power of 2 and then plug it out there. di to the power of 2 is equal to 1 over 2 If you plug this value out there, you will find this. Remember that in our virtual class, please remember that in our virtual class, we consider the case where both your mean and variance are variable, and then in that case, we show that gamma at si Sj plus R Si Sj is equal to R of Si Sj plus, I have to put 2 here and 2 here. In Si, R of Sj plus M Si minus M at Sj. Remember this relationship that we have in our virtual class? When your mean is variable, when your variance is variable, the relationship between variogram and covariance function is going to be this. If it happened that your mean is constant but your variance is not constant, this will cancel out. Because m is constant and this will cancel out. You are left with this. If it happened that your mean is constant as well as your variance is constant, then you can replace this with this. It will become 2, and you can divide both sides by 2 to get gamma plus r equal to r at 0. Because the separation distance between these 2 points is 0. The separation distance between these 2 points is 0 as well. Then if your variance is constant, if your mean is constant, then gamma plus r is equal to r plus 0. Remember that we argue that either gamma or r could have 3 scenarios associated with them. Your measure of variability or measure of similarity could be a function of absolute location. In that case, you have to specify 6 arguments in 3D to specify either gamma or R. If your measure of variability or measure of similarity is a function of absolute location, then that is called a dead end in geostatistics. You can go nowhere if your gamma or R is a function of absolute location. The next level of complexity is to have gamma or R a function of separation vector. Please pay attention, separation vector has nothing to do with stationarity or non-stationarity. You could have a stationary function, random function, where your gamma or R is a function of separation vector. The next level of simplicity, or for that matter complexity, is to have gamma and R a function of separation distance. Now, I would like to raise another question. If you open any textbook written on geostatistics, you will notice that they define variogram function to be variance of the first increment. Can you see any similarity between this relationship and this relationship here? In other words, under what condition this relationship is the same as this relationship? If you open any textbook written on geostatistics, sooner or later you will notice that they define variogram function 2 times variogram to be variance of the first increment. There is no 2 here. But today we try to dig further into this relationship, and we did realize that a measure of bandwidth is going to be the average of the square of these distances. What you need to do is to raise each distance to the power of 2 and then find the average. And then we show that this relationship is this, using this idea here. And now we would like to raise this question again. And we did answer this question while we talked about definition of variogram. Under what condition this relationship is the same as this relationship? Now the answer. If you define variance of a typical random variable to be expected value of x to the power of 2 minus expected value of x to the power of 2. That is definition of variance. Then you know for sure that here your x is going to be the first increment. What you need to do is to replace this x with this, and then you are going to have this variance of the first increment expected value of y at Si minus y at Sj to the power of 2. This is x to the power of 2 minus expected value of if you want to tell your audience how could it be possible to have this relationship to be the same as this relationship, you have to assume that this part is 0, which means that your mean has to be constant. Because the expected value of y at Si is m at Si, the expected value of y at Sj is m at Sj. If m at Si is the same as m at J, this will cancel out. Then the definition of expectation is to replace this expectation with summation. You could replace this by saying 1 over n sub k summation I from 1 to n sub k, and then because I need to have one index for the argument of this summation, I will change this to y at Si plus h minus y at Sj. Excuse me. That is how you could connect this definition to that definition. And for both of them, you have to put these two here. These two here. Do you follow me? If you want to figure out under what condition you could consider this to be equivalent to this or this equivalent to this, you have to have constant mean to be able to make these two equations equivalent. This part has to be 0. Please pay attention. This 2 here, Mr. Zahiri, has nothing to do with this 2 here. But this 2 here has something to do with this 2 here. And that is why I try to use appropriate editorial stuff to differentiate between this E and this E. This E here has nothing to do with this 2. However, this E here has something to do with this 2. Here you have to raise these to the power of 2 and then take expectation. Here you have to take expectation of this and then raise them to the power of 2. Here, if you raise this to the power of 2, you could still have variable, random number. And then you will take expectation. However, here, if you take expectation of this, you have a crisp number, not random variable. Do you know what I'm saying? Here, if you take expectation, you are getting a crisp number, no random variable, then raise this to the power of 2. Here, the argument is a crisp number. And then you will raise this crisp number to the power of 2. Here, the argument will be a random variable. And then you will take expectation of this number. Can you see the difference between where you have to put the power? Any question? Mr. Sabir Mir Ahmadi. Is it enough?
استاد یه سوال داشتم اون نقطه‌ای که الان ما داریم مثل با ردیف‌های پایین یعنی همیشه خطی دایرکشنال کلا یا تنبستگیش رو بررسی می‌کنیم.
Pardon me? We are talking about regular data. We have a possibility to have irregular data. See? Vector data. Where the data is no longer regular.
بعد اصلا جنس دیتایی که الان ما توی نرم افزاری الان بیشتر داریم یا پوینت یا کنترل لاینه یا دیگه الان میشه رستر رو
How about remotely sensed data?
نه توی
If you have remotely sensed data, then your data are raster based. But you are right. You raise in your Bachelor of Science, Master of Science, and then your PhD, you are more or less familiar with vector-based data. It might be a good chance for both the student coming from geological science and RSO, the student coming from civil engineering department, to start touching on remotely sensed data. Try to utilize or get benefit from remotely sensed data. It will add another dimension to your research. Now, Mr. Mir Ahmadi may want to know if our data are vector-based as opposed to being raster-based. How could it be possible to prepare H-scatter plot and then diagram function, covariance function, and correlation function? In order to make it totally different from what I said in my previous lecture on Monday, I would like to tell you how to prepare histogram in statistics. Preparing histogram in statistics is very similar to preparing variogram for vector-based data in geostatistics. If you want to prepare histogram for your data in statistics, how would you proceed? You are given a series of numbers, and the spatial location is not important for them because you want to go for univariate distribution. The very first item that you have to consider to prepare histogram is to delineate the maximum and minimum value in histogram. Delineate the minimum and maximum value. The first step. If you want to correspond this step in histogram preparation to the first step in variogram preparation, in variogram preparation, the first step is to delineate the maximum separation distance. Maximum separation distance in geostatistics is very similar to range in histogram. What is the definition of range? Maximum minus minimum. Therefore, the very first step in geostatistics to prepare experimental variogram is to delineate the maximum separation distance in your vector-based data. For that, you need to compute the distance matrix, and when it comes to maximum separation distance, try to write a Fortran program, MATLAB program, or whatever program that you can imagine to delineate the maximum value in your distance matrix. Therefore, the first step is to delineate the maximum separation distance, or L maximum. Now, The second step in variogram, in histogram preparation, is to discretize the range into a number of class intervals. Remember, in histogram plotting preparation, you have to delineate maximum and minimum values, subtract maximum from minimum to find the range, and then try to discretize the range into a number of class intervals. And you are familiar from statistics that if you want to discretize the range, you have an empirical relationship. What is that empirical relationship? The number of class interval P is equal to 1 plus 3 times 3 log of number of data. That is the relationship to connect number of class interval to number of data in histogram plotting preparation. All you need to do is say you have 1330 data, plug it here, find the logarithm of 30, multiply by 3.3, add it to 1 to find P. And this is empirical. You cannot justify this on physical or theoretical ground. Unfortunately, this subjectivity is very applicable to discretizing either the maximum separation distance or 2/3 of maximum separation distance. Here, instead of discretizing the maximum separation distance, we try to discretize 2/3 of maximum separation distance. And the reason for this inclusion, 2/3 of maximum separation distance, has something to do with the number of pairs toward the end of class intervals. As you notice here, if you take your separation distance to be h or 0, then the number of pairs is going to be equal to the number of data points. If you increase the separation distance to h, then you are going to have, say, 3 times 3, 9 data pairs. If you increase your separation distance to 2h, then you are going to have 6 pairs. If you increase your separation distance to 3h, then you are going to have 3 pairs. Which means if you increase the separation distance, the number of pairs assigned to each class interval will decrease. If this is your maximum separation distance, and you collapse it to 2/3, therefore it's going to be this. And then you would like to discretize this interval into a number of class intervals. What I am saying, we prefer not to discretize this distance at this distance, because if we discretize this distance, the number of pairs allocated to the last class interval will be very minimal, will be a small number, just like what we have out there. For 0 separation distance, we have 12 data pairs. And then it will increase to 9, and then 6, and then 3, and then nothing. Then you have 4h separation distance. Here, we should take a typical separation distance for class interval to be k. And this is the first class interval, this is the second class interval, third, and so forth. And if you consider this to be your final class interval, the name of this is going to be P. The number of pairs corresponding to class interval number 1 is N1. The number of pairs whose separation distance will be less than this, greater than 0. When you want to count the number of pairs corresponding to class interval 2, you have to say, I'm looking for separation distance whose numerical value is greater than this, less than this. And then if you call this to be H lower limit, this H upper limit, then for typical class interval like K, the number of pairs whose separation distance is greater than this, less than this, is going to be N sub K. And then when it comes to this N plus N index K plus 1, and when you are here, the number of pairs is going to be this. You can easily show that N sub K, K from 1 to P, the total number of pairs over the entire data set is equal to N times N minus 1 divided by 2. Could it be possible to check this formula, or perhaps I would say this formula when you have 2 points? If you have 2 points, what would be the total number of pairs? 1. If you plug 2 here, it will become 1. If you have 3 data points, here, graphical representation for the case when you have 2 data points is 1 pair. If you have 3 data points, then you have 3 pairs. If n is equal to 4, then you have to put n times 4 minus 1 divided by 2, that will give you 6. And if you have 4 points, then pair number 1, pair number 2, pair number 3, pair number 4, 5, 6. And you keep going. Now, maximum separation distance, 2/3 of maximum separation distance, discretize this to a number of intervals. You have 2 choices to discretize this separation distance. What are those 2 choices? It is very similar to what you have in histogram. In histogram, you could have equal class interval, or you could have variable class interval with different objective. If you assume that your class interval is the same, equal class interval, which means this distance is the same as this distance is the same as this distance, then the number of pairs allocated to each interval will be different. You could define a different scenario. In the second choice that you might consider is to consider variable class interval, but the number of pairs allocated to each interval is the same. let's see if we have this distance and we want to have 2 class intervals with equal class interval. When it comes to 2 class intervals, we have to subdivide the data into 2 pieces, the separation distance into 2 pieces. And depending upon the topology, the network configuration, the number of pairs in each interval will be different. What if we want to have 2 intervals with equal number of pairs? How could it be possible to proceed? Can you imagine? You would like to have 2 class intervals and the number of pairs in each interval to be the same. What you need to do is to, in order to find the class interval, the demarcation point, is to sort out your separation distance from minimum to maximum and then find the median. Half of your separation distance will be belonging to the first interval, the other half will be allocated to the second interval. What do I mean by median? Imagine that you have separation distance number 1 to be 2 meters, 5 meters, 7 meters, 9 meters, 12 meters. These are 5 separation distance in your data. Under what condition you are going to have 5 separation distance? What would be the number of data points? N to the power of 2 minus n minus 10. You have to solve this equation and hopefully you are going to get an integer number. If not, that means this 5 is not applicable. This is a quadratic function. And you have to solve this for n to find the number of data points to give you 5 pairs. Assuming that it is applicable, then you would like to tell your audience what would be the class interval. You have to demarcate this into this part. This is the first interval and this is the second interval. And the number of pairs allocated to each interval is the same. No doubt, you will say, what happened to this 7 here? You have to figure out how to discretize the separation distance into 2 class intervals with equal pairs. What would be my objective to play with these numbers? It is very similar to histogram. You could draw histogram in different ways. Even though I introduced this equation for the number of class intervals, but this equation is empirical. It is not theoretical. It is not based on physical ground. It is totally empirical. And then, as soon as you define your class interval, you have to count the number of instances in each interval for histogram plotting. And then, sooner or later, the instructor, the faculty member will tell you, please do not choose class intervals whereby you have data being bounded. Where should they be allocated? You should not discretize the range into class intervals so that a number of data points will be just on the interval, not belonging to the inside of each interval. به فارسی اونجا که هستید میگید هیستوگرام موقع میخواید کلاس اینتروالا رو تعیین بکنید باید کلاس اینتروالا طور انتخاب بکنید که داده سرگردان نداشته باشید. منظور از داده سرگردان چیه؟ یعنی داده نداشته باشید که درست روی مرز بیفته که ندونید تو این گروه بذارتش یا تو این گروه بشماریدش. We did write a number of papers touching on this point. If you want to prepare experimental variogram, if you want to prepare directional experimental variogram for a vector-based data, you have a huge number of scenarios to consider. And the question is, what would be the best variogram which could be representative of your data? Today, there is no answer for this question. If you find the answer to this question, then you are going to get there is 20 grade. Peace. There is no answer to this question that you are going to define the best situation. Which means that from as early as delineating the maximum separation distance, finding the 2/3 of this, then when it comes to this equal interval, you could have a trade-off between high number of intervals versus low number of intervals. If you take P to be quite high, then the number of pairs allocated to each pair will be quite small. It may happen that you have no pairs in a number of intervals for irregular space data. What would be the trade-off between low values of P, number of class intervals, versus high values of P, assuming that your class interval is equal? You could delineate papers written on network design, not for the purpose of getting average value right, but trying to design a topology to get best value. Try to delineate stations, rain gauge station, thermometer station, evaporation station, whatever station that you can imagine, to get best value. You could delineate papers to meet this objective. Unfortunately, there is no written document to tell you that if you are given a single series of data, the best discretization is going to be this, and then go ahead and find the experimental omnidirectional value. The number of pairs in this interval is n1, and then this interval corresponds to H scatter plot. And then when it comes to this interval corresponds to 2H scatter plot. Please pay attention. When you are out there, regular data set, the separation distance between each pair is the same. But when it comes to irregular data set, the separation distance for the first interval, all you know is that the number of pairs in it is n1. But you may have n1 separation distance, which are not the same. When it comes to this interval, you have n2 separation distance. Again, these n2 separation distance are not the same. They are very different. Then you could use this relationship to find gamma for each interval. In my Monday session, and in my previous lecture last semester, I touched on 3 measures for computation of H. Computation of gamma is this. You have to use this relationship. When it comes to computation of h for each interval, you have 5 scenarios. What are those 5 scenarios? Let me put it here. The very first scenario is to compute the separation distance in each interval using arithmetic mean. This is the first possibility. Computation of separation distance, representative separation distance for each interval using this formula. And of course, because I is defined internally, you have to define k externally. For k from 1 to t, that is the first possibility, to compute the representative separation distance in each interval. The second possibility is to compute representative separation distance using harmonic mean. That is how to compute harmonic mean.
H هر اینترولیه که از H آپرش کوچکتر از H نهاییش بزرگتر است.
These H1, H2 up to H and this K, not K, but and this n sub K, is all separation distance for which they are less than this value and greater than this value. If you want to specify lower limit and upper limit for this, then this is going to be H sub L1. This is going to be H sub U1. HL1 is 0. And it is cumulative. The third possibility is to go for geometric mean. Could it be possible to tell me how could it be possible to compute geometric mean of a series of numbers? Do you remember?
بعدشون بود به توان
This notation implies that you have to multiply H1 by H2 by H3 and so on. And then you have to raise this to the power of 1 over n sub k. Arithmetic mean, harmonic mean, geometric mean.
اصلا اولی چی بوده داشتیم؟
Pardon me?
اولی
Arithmetic mean, harmonic mean, geometric mean. And then you could sort out separation distance in each interval and represent your HK to be the median of separation distances. You have to sort out this data and then find the median. This is the fourth possibility. And then the fifth possibility is to say S of k is equal to S of L for interval k plus S of S of u k u minus, u k L k. If you simplify this relationship, because this will be factored out, simplified with this, you are going to get 1/2 S of Lu S of uk plus S of uk. The complexity of variogram modeling has something to do with these possibilities that you have. At first, you have to decide on the number of intervals, and this is up to you. And then you have to decide on the representative separation distance for each interval. And then as soon as you make this decision, you have a table like this. This is your S of k, this is your gamma S of k. For a variety of reasons, you cannot use this table to go for estimation. اینقدر این مسئله مهمی که علاقه من هستم به فارسی هم بگم. یه دانشجوی دکترا بعد از 6 ماه رو نتورک دیزاین کار میکرد. بعد از 6 ماه اومد گفتش آقای آقادینی من واریانس منفی میگیرم. خب توضیح بده چی کار کردی که واریانس منفی میگیرم؟ خب معلومه که من تخمینامو بر اساس این جدول تنظیم کردم. طبیعیه. یک داکیومنتی بهتون دادیم موقعی که کلاس‌های مجازی داشتیم، عنوان این هستش variogram.pdf. فکر میکنم تعداد صفحاتش هم نسبتاً زیاد. The number of pages is 10. Each page is allocated to a number of admissible covariance or variogram function. Then I will share a paper with you, a very interesting paper. It was written in 1984 in Water Resources Research, this paper. It was written by George Christakis on the problem of permissible covariance and variogram modeling. And in this paper, written in Water Resources Research, you have a chance to cover the entire course with this paper. The attractive feature of this paper is to tell you how to connect frequency analysis, converting spatial data to frequency data, mapping data from frequency domain to spatial domain and vice versa, to be able to touch on admissibility of variogram function and covariance function. You cannot focus on these tables to go for estimation. Let me see if I have time. No, I have no other additional time. On Monday, I will try to tell you how to proceed to represent this paper by theoretical variogram. And I will share this paper with you, written in Water Resources Research, to to be able to connect what I'm going to say on Monday and the reason why you have to convert this experimental variable to theoretical variable. از حضور همگی سپاسگزارم. تا روز شنبه همگی رو به خدا بسپارم.